You ready for this? You ready for some statistics? Let's do it.
Hold on to your butts.
Y'all remember what movie that's from? One of the few Samuel L. Jackson sound bites I can actually do during class without getting in trouble.
Hold on to your butts.
Let's do it. So, what are we doing today? Ah, yes. If you watch the video, you know what we're doing today. We are actually going to calculate the one sample Z interval confidence interval for proportions. All right? Otherwise known for short as the 1propZ interval. All right? Prop stands for proportion, the 1propZ interval. So it's a 4-step procedure. You've done 3 of them, right? In the video, you did the state part. All right, that's the context. What are you doing? You did the plan part. That's where, you state what you're going to do, what calculation you're going to do, and you check the conditions for inference to make sure you're actually allowed to do the thing you want to do. Today, right now, we are doing the do. Do the do. Mountain Dew. It gets such a bad rap. We are going to do the do part today. And of course, you've done the conclude. You can write the sentence to analyze and interpret the confidence interval. So we've got that done. So all we have to do are the calculations. We're going to do this procedure for any confidence level, not just the 95 and the 99.7, but we are going to sort of start there. Those are the easiest ones. Okay? So let's do this, ladies and gentlemen. All right. So again, the basic setup for a confidence interval. All right. You take your point estimator, p hat. You add and subtract the margin of error. All right. That is the basic confidence interval formula. Now let's break it down a little bit. What is the margin of error? Well, a p hat plus or minus. How do we calculate the margin of error? Well, that's our z star times the standard deviation. All right, how many standard deviations are we going out? Now there we run into a bit of a problem, okay? The standard deviation is based off of the population proportion. Let me pull up the statistics formula sheet here for us. All right, hopefully this looks a bit familiar. We've used it quite a bit. Where's the draw? There we go. So the standard deviation right here of a sampling distribution for proportions is based off of the population proportion, P. But we don't know the population proportion, right? That's why we're taking a sample so we can get an interval for where it might be. So what do? Well, we do the next best thing. Okay, if we don't know the population proportion, we're going to use the only proportion we have, which is p hat. Okay? We don't know the population proportion, so we're just going to use the sample proportion instead. It's the best we can do. Now, because these are technically 2 different things, they have different names. All right, this is the standard deviation on this side. But when we do the sample version, we call it the standard error. Just to differentiate between the two. All right, it's an estimate of the standard deviation, because technically the standard deviation uses the population proportion, which we don't know. Okay, so the equation's the same. Hopefully you can see the formula is the exact same. The numbers go in the same place. We just have to use p hat instead of p because we don't know p. Now, I should call attention here. This little asterisk means there's a note at the bottom. So let's go scroll down to the bottom. What does it say? The standard deviation is a measurement of variability. All right, we got that. For the theoretical population. The standard error is the estimate of the standard deviation. Okay, it's as good as we can do with the sample. If the standard deviation of the statistic is assumed to be known, so if you know the actual standard deviation, then you should use the actual standard deviation instead of the standard error. But what the heck did you just say right now? All right, so if you remember the problems on your last exam on sampling distributions, sometimes I would give you both the population parameters and the sample statistics. So you would have a proportion for the population, the true one, and you'd have a proportion for the sample. Now before, we didn't have to think about this too much. You just always used the population proportion. And if you still get a problem, you should still use that population proportion if you have it. If you don't have it, if all you have is the p-hat, the sample statistic, then of course you have to use it. But you never want to use the sample statistic when you could have used the population proportion, because the population proportion is better, okay, because it's the true one. But the formula is basically the same, okay? All right, let's write that down. The standard error, so this we're going to approximate with the standard error. So we're going to do p-hat plus or minus z star times the standard error, SE. And so our standard error is equal to, the equation sheet calls that S sub p-hat, the standard deviation of p-hat. I've seen both in textbooks, so you should probably be familiar with both. It is the square root of p-hat times 1 minus p. I like the q. I don't know. I've been using p and q a lot. I like p-hat, q-hat, because then it kind of looks like a face, and it's kind of funny looking. But looks like a cat now, doesn't it? Meow. That's the sound effect I need. I should get a cat sound effect. That's what Bolt's doing during lunch. All right, so we're going to use that formula for the standard error right over here. We know kind of how to get z star a little bit, at least for a 95% confidence interval. We should now have all the tools to actually do a confidence interval by hand. Let's do it. All right, so you've done most of this problem already. If you watched the video, this is familiar to you. So a recent poll of 738 randomly selected cell phone users found that 170 admitted to walking into something or someone while talking on their cell phone. I've never done it. I've heard it can happen. I've never done it, though. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. So in the video, you did the first two steps. You did the state part, so I don't want to go over that. All right, go watch the video. We did the plan part where we had to check all the conditions for inference. Again, we've done that in the video. You hopefully have that in your notes, right? I want to focus on doing the do. Can we actually now calculate this confidence interval, the actual calculations? So remember, we're doing a 95% confidence interval here. So we're going to take our, in the formula here, p-hat plus or minus the margin of error, which is z star times our standard error. So what are all these pieces here? Well, what's p-hat? The proportion. It was 170 out of 738. So 170 out of 738. What is that? 70 divided by 738 gives us a proportion of 23%. 0.23. All right. What is the z star? Now remember, that's how many standard deviations are we going out. It comes from our confidence level. If I want to be 95% confident, I have to go out 2 standard deviations. Caveat, it's not exactly 2. That's an estimate that we use because it's easy to memorize. We'll talk about the exact value in a few minutes, but 2 for right now is a good estimate. And last, we need the standard error. What is the standard error? It is the square root of p hat times q hat. So 0.23 times 77, right? Yeah, 0.77 divided by our sample size, which is 738. All right, we've got all the pieces. Let's plug them in. So p hat is 23%. That is our point estimate. We're going to add and subtract. Remember, I should make a note. Be a good stats teacher, Bolt. This whole thing is the margin of error, right? That's the margin of error. Just good vocabulary practice there for us. Plus or minus 2 times... I'll show all my... I might as well put the whole thing. If you want to see the whole thing as one big formula, might as well, right? 0.23 times 0.77 divided by 738. That's going to give us our interval. So now we have only numbers. It's just plugging this into the calculator. I might do a couple of steps here, but it's kind of up to you how many steps you want to break this down into. Just be careful with the order of operations, all right? So I'm going to do 0.23 times 0.77 divided by the sample size, 738. Then I have to square root that number, so square root that number, second enter. Then I have to multiply that number times 2. So this is my margin of error, 0.031. So I just did that whole thing on the calculator. Be careful with order of operations, just to make sure you don't make a mistake. So now we've got to type this into our calculator. That takes 2 steps to type this next one into a calculator. So 0.23 plus that number, 0.031. So we got 26.1%. And then 0.23 minus that number, 19.9%. All right, there we have our confidence interval. Sometimes you'll see it just written like this as an interval, 19.9, comma, 26.1. Either of those are perfectly fine representations of that confidence interval. Which hopefully that is pretty darn close to what we got in the video. I think they rounded up to 20. They went from 20 to 26, but that's just a little round off error. Basically the same thing. All right, hoping that process there makes sense. You should have the conclusion written in your notes already. I'm pretty sure we did that in the video as well. We are 95% confident the true proportion of whatever the heck the context is. Cell phone users who would admit to walking into something. The true proportion is between those 2 numbers. All right, somebody asked me a question. Anybody? You feel like you got this perfectly? There's nothing you don't know?
They don't know that we know they know we know.
All right. Let's see if you got that. All right. Synopsis then. All right. Can I go over how you got Z again? There we go. I like it. All right, so the Z star, you only know a couple of Z stars right now, okay? You only know a couple of those. If it's a 95% confidence interval, that means you have to go out plus or minus 2 standard deviations, okay? That's because of the empirical rule, you know, we learned that a long time ago, but it keeps coming up, all right? If you go out 2 standard deviations plus 2 SDs minus 2 SDs, that is 95% of the data. Okay, so that's one Z that we have memorized. The other one you have memorized is the 99.7% interval, because to get 99.7% of your data in a normal model, it would take plus or minus 3 standard deviations. So right now, those are the only two Z's that you could do. Now, after you practice this process a couple of times, I am going to show you how to find all the others if you wanted, say, a 90% confidence interval. All right, it's 1 point something. I'll show you how to find that, but you don't know quite yet. What did I do in the beginning? I woke up and I got out of bed. No. In the beginning, so I started with the basic formula. A confidence interval at its most basic is the sample statistic, the point estimator, plus or minus Z standard deviations, or Z standard errors, since we're estimating the standard deviation with the standard error. We're going to take our point estimator and then go out a certain number of standard deviations. Okay, and then we had to plug in our Z, which was 2, because we're going out 2 standard deviations to give us 95% confidence. Then we have to plug in our standard error, which is just the formula. Okay? P times Q divided by N, and you square root the whole thing. So the 23 came from P hat. Now we had to calculate P hat because they didn't give us the proportion. So I had to calculate the proportion successes divided by the sample size, 23%. That lets you get Q, which is the other side of that proportion. Put that together, you get the margin of error. Right here is the margin of error. Then you add and subtract that to your point estimator to get your interval. All right, I want you to try that to see if this is making sense. And maybe as you're trying it, you'll get a few more questions. I need to draw. There's my, all right, period 3. Copy link. Q is 1 minus P. So let me pull up the... So in the formula from College Board, they always say 1 minus P. Right there. I think it's more elegant to say the square root of P times Q over N. I think, but Q is 1 times P. Sorry, 1 minus P. Some textbooks use this way, some textbooks use that way. They're the same thing. All right, so the first 4 slides, I think. Let me double check. The first 4 slides. Yes, slides 1 through 4. Same process, same idea. Do the calculations for a confidence interval. Feel free to keep putting questions in chat, and I'll answer them there. But try those out. Alrighty. So on that last one, slide 3, the interval was about 29% to 37%. Somewhere between 29 and 37-ish, depending on how your decimals went, for slide 3. Slide 4, why is that argument not valid? All right, he's like, yeah, we did billions of sales. You only checked 1,000 out of 1 billion. That doesn't seem like anything. That doesn't matter. The size of the population doesn't matter. A lot of what you were saying is like, hey, we're 99% sure, confident. I like that argument. To take that one step further, the reason why we really know this is true for the whole population is because we randomly sampled. Okay, this goes back to first semester. If you take a random sample, your results can then be applied to the whole population. If you truly took a random sample, they can't say, nah, you just got a bad batch. All right, you just checked that one city was no good. Well, no, we didn't just check that one city. We randomly sampled from the entire population. And so if you randomly sample from the whole population, it doesn't matter how big that population is. The random sampling takes care of that. And then the fact that we took 1,000, I mean, the chances of getting one mislabeled fish thingamajig, probably pretty high. The chances of getting 1,000 of them, though, if you're randomly sampling, nah. So that's why our results are valid, because we randomly sampled, and all the other conditions. So those of you who mentioned, oh, the 10% condition, all those stuff had to be true as well. They were true. And so that argument, while it seems good at first, and it seems good to someone who doesn't know stats, that's not how it works. Because we randomly sampled, we can apply our findings to the entire population. And we're 99.7% sure. Which is pretty high. All right, but moving on from 99.7, how do we do the other ones, Bolt? What if I don't want to be 99.7? What if I want to be 98% sure? What if I want to be 90% sure? All right, how do I do the others? So let's take a look. Come back on over to my screen. Let's do the others. It's not that hard. Your calculator is going to do it for you. I just got to remind you. You already know how to type it in, actually. I just have to remind you how to type it in. So, real quick, the ones that we kind of know, the 95% confidence interval, where did that come from? Well, we got that number by looking at the normal model, right? And we asked ourselves, how many standard deviations do you have to go out for you to get 95% of the data, right? And then we found these endpoints. Now, those endpoints are essentially +2 and -2. Now, it's not perfect, though. It's actually not, it's not exactly 2. It's a little bit off from 2. So how do we find the actual number? Well, I know the percent is 95%. How do I take a normal model and go from a percent to an endpoint. You remember? How do we go from a percent to an endpoint on a normal model? Inverse norm. All we have to do is do an inverse norm. Now, what numbers do we plug in for the inverse norm? Well, the area is 95%, so 0.95. What's the mean and the standard deviation, though? So this is the standardized model of the normal model, the most basic normal model. The center is 0. Oh, I talked about it. Hopefully I went over slide 4 a little bit. Ignore it. I try. No, just kidding. Don't worry, Nato. We'll go over it in the next lesson, okay? I'll make sure I cover it in the next lesson for you. All right, so the mean is 0. And the standard deviation is equal to 1, okay? 1 standard deviation, 2 standard deviation. All right, we're counting by ones for the standard deviation. All right, so that is the most basic normal model right there. That will give us how many standard deviations, how many standard deviations we have to go out, okay? Oh wait, not area 95. We want 95 in the middle, right? Shoot. Not everybody's calculator can do a middle, can they? So if your calculator can't do a middle, then you have to think, all right, how much area is to the left, right? I think 84s can't do a middle. So if you want the area to the left, how much area is to the left? So you got to do a little quick math. Well, if 95% in the middle, that's 5% left over. That means there's 2.5 right here, and there is 2.5 right there. Okay, so if we want this endpoint right here or this endpoint right here, we have to either use 2.5, or if you add the 2.5 plus the 95 to get this endpoint, it is 97.5. So let me show you that real quick. First on the 84, then we'll do the Casio. All right, so we go second distribution. We want number 3, inverse norm. So the area. So the area to the left. The 84 always does area to the left. So 0.025. I want the boundary to have 2.5% to the left. The mean is 0. The standard deviation is 1. All right, type that in, hit enter, hit enter. So we had to go over 1.9599. So we usually round that up to 1.96. Okay, now we're going to add and subtract that number. So they gave us the -1 because we had to go to the left. But the number you want is 1.96. So here, the Z star is technically 1.96. But you can see why we usually use 2 as the option. All right, let's pick another one. Let's do an 80% confidence interval, shall we? What if we want to do an 80% confidence interval? So we have to do some quick math. All right, we got our normal model here. Okay. I want, the mean is always 0 for this, yes. For this one, the mean is 0. If you want a Z star. The mean is 0 and the standard deviation is 1. That way you're counting by ones on your standard deviation scale. So the mean is 0. So now visualize this. I want 80% in the middle, right? If you're calculating a critical value, then yes. The mean is 0 and the standard deviation is 1. If I want 80% in the middle, that means on the left and on the right, there's 10% left over, right? Because it has to make 100. So if I want to type this into my 84, I have to type in this one, 10%. That will give me how far away from the middle I have to be. So let's do that real quick. I'm going to go second distribution, inverse norm, 10%. So 0.10, 10%. Man, you have to enter. Negative 1.28. So my Z number is the 1.28. Where we add and subtract that number. So you can think of that number as both positive and negative, since we're going to add and subtract it anyways. That Z is... Oh, I didn't do it on the Casio. My bad. I'll do it on the Casio real quick. Where'd my Casio go? I don't think I have it up here. Casio. All right, so I go statistics, distribution, normal, and then I want inverse norm, so that's F3. All right, so here, if you want to be if you want to do a central, you can do the center. That's actually a little bit easier for you. Then you're doing the area in the center. So for a 95% confidence interval, we'll put 95 in there. The standard deviation is 1. The mean is 0. And there you get the 1.96. It's good in many ways. It really is. And then to do the other one, you can do the central. If you want 80% in the middle, it gives you the one, and it gives you both the negative 1.28 and the positive 1.28, because you're going to do both anyways. But that's how you can get any confidence interval you want. Okay? That's how you can get any confidence. So let's do one of those together real quick, and then I'll have you try one on your own. We're going to do the same story that we did with the cell phones running into things. But instead of doing a 95% confidence interval, let's do a 98% confidence interval this time. All right, a 98% confidence interval. So let me list out all my, again, my p hat was 23%. All right, so I'm going to do 0.23 plus or minus. All right, what is my Z star number going to be? How many standard errors am I going out? How many standard deviations am I going out? So I go to my calculator. I go inverse norm here. All right, so if I have 98% in the middle, that's 1% on either side, right? So I'm going to go 0.01. There's 1% on either side. This is the area to the left I'm actually typing in here. Mean of 0, standard deviation of 1. Paste that in. Enter, enter. Negative 0.2326. I might go all three decimal. You could go, no, 2.33. Just round up the 2. So 2.33. That's a lot of 2s and a lot of 3s, isn't it? 2.33 times the square root of p.23 times q, which is 0.67. 7. Yeah, all right, I'll do that one more time. So where the heck did this number come from, right? It is a 98% confidence interval. That means there's 1% on either side of the normal model. 98 in the middle, 1 on the left, 1 on the right. So I'm going to inverse norm that 1%. So second distribution, inverse norm, 1% to the left. There's 1%. The 84 only does to the left. All right, to the left, to the left, to the... No, just to the left, to the left. All right? Just to the left. 0, 1, paste. Negative 2.33. That is our Z star. On the Casio, you have to put the confidence for the area. Yes, I think that's a little easier. You want me to do it on the Casio? Yeah. Well, you can do it that way. I mean, if you want to do it the way I did on the 84, you could just say, hey, instead of central, you could put left. If you wanted to, you could put left. But yeah, I think it's definitely easy. Do center, and then you'll put the 0.98. So we have 0.98 in the center. Mean 1, standard deviation. Definitely one of the reasons why I like this cap. It's cheaper than the 84 too. Can you believe that? It's like cheaper by like $50 or something like that. And then you get, and it gives you both of them, the negative 2.33 and the positive 2.33. All the other calculators do this though. So if you have like the prime or the Nspire, they all do this as well, just slightly differently. You might have to Google it or ask me during office hours. All right, what was the number on the bottom? 738. But then this is all the same. I don't need to actually do this for you. This is all the same as it was before. We just have to type this into the calculator now to get our answer. All right. I might as well do that, huh? Let's see. So 0.23 plus or minus. What is our margin of error? So 0.23 times 0.77 divided by 738 equals that number square root that answer. We get that times 2.33. So our margin of error is 0.036, 3.6%. Add it and subtract it. So 19.4 to 26.6. There we go. Which, hopefully it makes sense. That interval is now wider, right? Would 0.04... I maybe wouldn't do 0.04. I maybe wouldn't do 0.04. I know 6 technically rounds up the 3, but I think that would get you kind of far away from the 98%. I think because the differences in the Z values is so small. Well, no, 0.04 is probably good enough, isn't it? Although if I do 0.04, that would be 27 to 19, wouldn't it? And then that interval would be almost exactly the same as before. No, not quite, I guess. Because that's basically 20 to 26. It would be at least different than the 90%, 95% confidence. You'd probably be fine. You'd probably be fine. Great answer, Bolt. You say no, then you say okay, then you say no, then you say okay, then you say no. Make up your mind, man. Come on. Again, this is not calculus, all right? If you show your work, you will be okay, I'm guessing. All right, if you had this and then this, I think you would be fine. It's obvious what you were doing. We are not crazy about 3 decimal place accuracy in stats. All right, that's not a thing. Kind of nice that it's not a thing too, but all right. Hoping that makes some sense for you. Try it. Can you try at least get maybe slide 5 done? We got 5 minutes or so. Try to get 1 done. If you don't get all the way to 7, that's okay. But try to at least get 1 of these done so you can practice it on your own without me at least once, okay? Try at least 1 out. Hopefully it's getting kind of fast. It's not that hard to do to crank one of these out. Again, you don't have to write down everything in the slide for me. I know that's tedious, but give me a little bit of what you're doing.